All right. So if you're seeing this, this means you are one of the people that gets to learn about naming transition metals as well as going from the name to the formula. So this is going to be a little bit longer than the past two videos we've watched or that you've watched and done notes on just because of the nature of naming transition metals. So here we go. Transition metals transition because they can form many different ions. So example would be sodium is always Na+1 because it's in group 1, and group 1 metals have one valence electron. Therefore, they lose one electron to be stable. So they're normal. They can only form that one ion. But then you've got something like iron that is a transition metal that can be iron +2 or iron +3. Kind of depends on what it's being bonded with. Because you can't determine the oxidation number from the periodic table, a Roman numeral is used to show it. So for example, Roman numerals, if you don't know what those are, I will give you guys a list later when you guys go to actually practice this. 1 through 10 would be sufficient, just fine. But this is a Roman numeral 1, this is a Roman numeral 2. So this is copper 1 and copper 2. And then so this is what it's going to look like, Cu+1 and Cu+2. So let's go ahead and talk about the second I cannot talk this morning. The second exception to naming ionic compounds. We're going to start with the formula and go to the name. So you're going to write the name of the first element, which is the metal. The exception here is if it's a transition metal, which means it's in groups 3 through 12, include a Roman numeral to indicate the charge of the metal. So that would be the exception. So you're just adding the Roman numeral in the middle. Then you're going to write the name of the second element, which is the non-metal with an IDE ending. So again, we're going back to that original rule with the number 2. That one didn't change this time, which is kind of nice. So some examples of this would be copper and chloride. The name would be copper 1 chloride. Here we have CuCl2. This is actually copper 2 chloride. So you can kind of tell based off of this subscript here what the Roman numeral is going to be. Okay, so let's go ahead and start talking about determining the Roman numeral for transition metals. There's 2 different ways. Option 1 is to reverse crisscross, which is what I essentially just did in the previous slide. I feel like that's the easiest, just because you literally can just backtrack what you do when you go from a formula or from the name to the formula. The second option is to use visuals or math to determine what charge of cation must be for the overall charge to be 0. So regardless of which option you prefer, always double check that you're correct. Always, always, always. So for this example, we have 10 and phosphate. So yes, you can have your polyatomic ions connected to transition metals. So those would follow exception number 1 rules. So to do option number 1, 10, you're going to reverse crisscross with phosphate. So phosphate we know is a -3. That doesn't change. We know that. So basically we got that from the subscript that's behind 10. And then we can basically do the reverse. So phosphate outside of the parentheses has a 4 as its subscript. That means 10 is 10,4 phosphate. For option 2, this one involves a little bit of visuals. So let's pretend we have 3 10s. So we have our 10 set up with the dots with the question marks. And then we have 3 phosphates with a -3 charge. So the question mark is the charge that you're looking for. And this is the charge on the phosphates. So we already know there's 4 phosphates with a -3 charge. So 4 times -3 would be -12. And then it's basically a little bit of algebra. So 3 divided by +12, because we know it has to be positive for it to be a metal. Obviously, we know that. You do 12 divided by 3, you get +4. So there we go. So then you still get the same answer, 10,4 phosphate. In my opinion, this is the easier option rather than the visual option, but it is up to you which one you would prefer. This takes up way less room compared to this one. So all right, so we're going to go through this portion again with example number 2. So for example, number 2, we have iron and sulfate. So with option 1, we're looking for what the charge is on the iron, and sulfate already has a set charge at -2. So if you reverse crisscross, the 2 should be there, but this should be an immediate like, oh, okay, this must be this, it must have the same charge, because for 1, there is no parentheses around sulfate to tell us how many there are, and then there is no subscript outside of the iron either, or right next to it. So that should tell us that it's been basically reduced. So we can basically say that since the 2 isn't there on either side, it must have been reduced. So these are harder, but it would be still iron 2 sulfate. So it's just kind of thinking a little bit harder about what the charges would be, and kind of thinking backwards in the sense of how you would get your charge. Option 2, here we go. We have at least one of each. 1 times -2 is -2. We know this has to be +2, so 2 divided by 1 would give us +2. It still gives us iron 2 sulfate. So again, your choice which option you would prefer to do. In my opinion, this is the easiest, but when you have something like this that you don't see the subscripts on the outside, this may be your better option, just so you can visually see it. Totally up to you. So let's go ahead and practice this. You've got 5 different examples here. Go ahead and pause, figure these out, and then I'll give you the answers in just a second. Okay, so number 1 is iron 3 chloride. Number 2 is chromium 2 oxide. Number 3 is manganese 7 oxide. 4 is chromium 3 nitride. And 5 is silver 1 sulfide. So now we're going to go from the name to the formula. So we're going to write down the ions in each element with its charge, aka the symbol with the oxidation number. So for this, the transition metals charge will be given by the use of Roman numerals. So the Roman numeral, let's say it's a 2. That means it's a +2, okay? So iron 2 oxide is our example here. So we know iron has a +2 in this instance, and oxygen has a -2. So we're going to determine the number of each ion it takes to make a compound with no charge. So we're going to do the crisscross applesauce method. We've been doing this entire time. So again, you're going to cross and drop that charge, make it where those numbers are your subscripts. You're going to write down the formula using those subscripts to show how many of each ion it took. So you have Fe with 2, O with 2, and then you can reduce and simplify as needed. And we know that based off of the fact that they both have the same subscript, we can reduce. So that gives us this as your final product. Okay. Now let's go ahead and practice this. So these are going from the name to the formula. Go ahead and pause, see if you can do this on your own, and then I will give you the answers. So number 1 looks like that. Number 2 looks like this. Number 3 looks like this. Number 4 looks like this. And number 5 looks like this. All right, if you guys have any questions, let me know. I am here to help, but otherwise, let me know.